at the end of this set of discussions, I would like to revisit Kepler's laws of planetary motion, and in that I would like to tell you about I told you that Tycho Brahe was the man who was fascinated by the wanderers, the planets, and he made several hundreds of sheets of observations with naked eyes, looking through a bamboo as his only help. So Tycho Brahe was a very moneyed man, and he had lots of estates, and he wasn't worried about money at all. So he dedicated himself to the study of the planets, wanted to know as to what is there. Later on, he appointed Johannes Kepler as his assistant, who naturally, as a young man, stayed with him for a certain period of time, because the birth of Kepler and the death of Tycho Brahe, there is a difference of 30 years. So that means that Johannes Kepler, maybe at the age of 18, 20, he joined him, and he tried to assimilate, to analyze, to synthesize, and to work out the work of Tycho Brahe. Plus, he made his own observations. Now, these years, they go with Galileo, the Italian scientist, father of modern thoughts in physics, and Galileo outlived him by 41 years. Interesting that Newton was born in the same year Galileo died. Okay. 1642 he was born, and 1727 Newton breathed his last. There was an older man, Copernicus, who gave the idea of a heliocentric system. He died before Tycho Brahe was born, before Galileo was born. And in his studies, Copernicus thought that our planets, they move in circular orbits. Okay. Now these days we are in quarantine, and we have the coronavirus, which is affecting our lives. Similar thing happened in 1665, when there was great plague in Britain, and all institutions, etc., were closed. Newton, he went back from his college in London to his mother's place, and in 1665 the apple fell for the first time. Okay, that's a story doesn't fit with a great personality like Newton. Of course, the apple did not fall on his head, and gave him the ideas that he later on gave in his Principia Mathematica, etc., etc. Okay, so the first law of Kepler is the law of orbits. And what Kepler suggested was, from his calculations, that the data of Tycho Brahe, they fit elliptical orbits rather than circular orbits. Sun is at one focus of the ellipse, or one of the foci. It's musical if you call that Sun stays at one of the foci of an ellipse. Now, an ellipse which has not been drawn very properly here, we have two axes which split the ellipse into two equal halves of areas. One of the axes is POA, where O is the center of the ellipse. So that PO and OA, they are equal, and they are supposed to be equal to A. Let us call it, say, A, and this is called a semi-major axis. A semi-major axis. Okay? A semi-major axis. And similarly, OB equal to OC, that is called B, and it is a semi-minor axis. Okay? A is called the aphelion and P is called the perihelion. P is closer to S. This is the situation of the Sun that we have chosen. It could have been another position of the Sun over here. Now, with this, the planet goes like this about the Sun. There is a time in the planet's journey, for example, if the planet were Earth, then in the month of January, the distance from the Sun to the Earth is maximum. What month? In the month of January, around that time. And in the month of that is December, January, and in the month of June, it is closest to the Sun. Long back, around more than 40 years, when I was teaching this for the first time to the students of class 11th, when class 11th used to be taught as a pre-university class in my university, I was chosen as one of the teachers in some 10 odd sections. And one of the students, he said, "How can it be possible, sir? It's not possible that this is the position of the Earth. In the distance between the Sun and the Earth is maximum in the month of," what I said? In the month of January. And minimum in the month of June. And he said that the weather reports say that it is cold in the month of January and hot in the month of June. And he thought, and he argued, and thereafter many teachers also argued with me that, that yes, it should not be there, but actually they forgot that in the southern hemisphere during the month of January, it is summers, and during the month of June, it is winters. So that what is the temperature at a certain point on the earth, because of the position of the sun, the important point is that the rays, they come straight or they come slanted. So the weather is done like that. Okay. Now what is an ellipse? An ellipse can be drawn with considering the two foci, and if there is a string and it is a stretched string, so F1, Q, F2, that is the length of the string, and if that string is taken around, then the ellipse emerges. This is given in the books, you can know that. So the second of the three laws of Kepler is called the law of areas. In fact, it is the law of areas. We can say that there is a conservation of angular momentum, or that there is no change in the value of angular momentum, and it's because the force of the sun on the planet is a central force. Okay, the law of areas is like this. The line joining the sun to the planet is here, and we are taking very short interval of time. Okay, the line joining the sun to the planet sweeps. That line is a sweeper. Sweeps equal areas in equal intervals of time. Okay, equal areas in equal intervals of time. Now, this we are talking about. The planet is moving in a surface. The area I have shown here, and here also, area is a vector quantity. I told you area is a vector quantity because of the cross product of two vectors. This is the length vector and this is another length vector. When it is this is swept toward this, we get a parallelogram, and the direction of the parallelogram, the area is like this. I also asked you one day that can you give me a single page of paper, and the answer turned out that single page does not exist. It is a leaf and which has got two surfaces, and therefore we get a couple of surfaces, and on either side of the surface there is a normal. On this side the normal is pointing towards you, on this side the normal is pointing away from you. Okay. The two sides. Now what is observed is, because of the aphelion being farther than perihelion, which is closer to the sun, it is found that the planets move slower when farther from the sun. Slower means their velocity is very small. And the planets move faster when the planet is closer to the sun. Okay, from the sun. The distance from the sun is smaller. Now, law of areas is a consequence of the conservation of angular momentum L. So let us see what will the area swept in time delta t. Let us go to this figure, and we find that the area is R, okay, cross P, and then half of it, because this is the triangle, so this is the distance, and we find out from geometry that the area circle the time delta t is equal to delta A is equal to half R cross B into delta V into delta t. Okay, half R cross V into delta t. Now this V can be said to be equal to the vector P, which is the momentum vector, divided by M, which is a scalar. If I substitute that over here, then I find that this, I divide this equation this side by delta t, so the rate of change of area, okay, with time, that turns out to be half R cross P upon M, which is half into L, as R cross P is equal to L. Okay. Now, the force that exists in gravity is a central force. The force is towards the focus over here. We can say that this is the central force, and therefore in central forces the angular momentum is conserved, and so we can say that the equal areas are traversed in equal intervals of time, and this is vivid from the drawing. The two delta t intervals are just shown. Over here you can see the distance that has been covered by on the path of ellipse is smaller as compared to here, which is larger because the P is closer to the sun. Yes. This is true for all planets. I have not shown the other focus. The sun could be here also. Then in that case the P will come over here and the A will go here. Okay, so we can therefore show that the equal areas are swept in equal intervals of time, which is the consequence of the law of conservation of angular momentum. Now we go to the third law. We studied the law of orbits and the law of areas, which was nothing but a conservation of angular momentum. Now if we further that at the 2 points aphelion and perihelion, then I can write from the studies that we have made that LP will be equal to M into RP into VP, okay, and LA will be equal to M into RA into VA, and the two will be equal. So I just write them like this: M RP VP is equal to M RA VA. This is the mass of the planet, and so on the two sides I cancel that, and therefore I write the ratio of the two velocities at the perihelion to aphelion. Vp upon Va is equal to Ra upon Rp. This follows from this relation, which means that if Ra is greater than Rp, then Vp will be less than Va. Okay, so the velocity at A will be less as compared to the velocity at P, and so this is the consequence of the second law. Now I introduce to you the third law, which is called the law of periods, which is T square into is proportional to A cube, where A is the semi-major axis, and it is just like the T square into R cube, in the case of satellites that I proved in the case of satellites the other day. Now, I have the natural planets nearest to the Sun is Mercury, then Venus, then Earth, Mars, Jupiter, Saturn, Uranus, Neptune. I am just writing the name of Plato. Plato has been recently considered as not to be a planet at all. Okay, so I am not telling you the data regarding this. If we measure the semi-major axis A for the Mercury to Neptune in 10 to the power of 10 meters, okay, that is 10 gigameters, that is the unit. Then for Mercury it is 5.79, Venus 10.8, Earth is 15.0, 22.8 for the Mars, Jupiter 77.8, Saturn 143.0 or simply 143, Uranus is 287 and Neptune is 450.0. Now, this is the semi-major axis that was measured, and these data were available to our friend Kepler, the beautiful mind in those times. And then the time period was also studied in years. For Earth it is 1 year, and for Mercury it is 0.24 years, then keeps on increasing, 0.615 for Venus, 1.88 for Mars, 11.9 for Jupiter, 29.5 for Saturn, 84.0 for Uranus, and 165.0 or 165 for Neptune. Okay. Now, this beautiful mind called Kepler, okay, he calculated T square by AQ for the individual planets, T square upon AQ for the individual planets, and his calculations yield, we find, I am not giving those values, you can look into the books, but that varies from 2.95 to 3.01, okay, into 10 to the power of minus 34 year square per meter cube, okay. So you see that this is more or less constant, and therefore T square upon AQ is a constant. So he could prove, we could find that T square, the square of the time period, is proportional to the cube of the semi-major axis. Now with that, we come to an end of my lecture series under the umbrella called gravitation, okay, and studies. Well friends, hereinafter I will talk about materials, solids, fluids, gases, and the physics which involve them. As I told you on that day, that a solid can be converted with provision of heat to it, and it melts down, and we have a fluid which we call liquid, and if the temperature is raised and the average kinetic energy of the molecules of that system increases, then ultimately the vaporization starts taking place. This is the same material, but the material exists in three forms. In fact, from time immemorial to this day, I think more than 80% of the researches that have been conducted by scientists from bygone era to date, that concerns materials, and that together is called material science. So one of the things associated with materials that you know about, and that is elasticity, which is in the form of Young's modulus, bulk modulus, and the modulus of rigidity, etc., and which is used in many engineering application, not only in mechanical engineering and civil engineering, all kind of engineerings and technologies, they require the study of materials, the behavior of materials. Even in the case of electronics, we see as to how many electrons are available in the said conductor or in the said semiconductor. So I'll talk about all these things in the coming lectures. Well, you question, we answer. I'm happy that some people have done so. I would like you to add to them, and I'll be glad to discuss out the things with you. Okay? Even if involves not doing physics, but doing the history of physics, history of science, history of technology, history of mathematics, etc. in the due course of time. So I have enjoyed, and I am going to enjoy more, because this subject of materials is a subject which I like the most. Okay, and I will share my experiences out with you as easily as possible. Thank you very much, and see you again.